welcome everybody. So last Wednesday we looked into how database systems are used, in particular in the context of the cloud. We had this stacked architecture I explained at length. Today we will look inside the database system, in particular at the interfaces, the outer interface of the database system. So how do people use the database system, which functions are available, and why should we worry about that? And then we look a little bit also into the internal structure, the high-level structure of a database system. That doesn't, whatever I explain doesn't mean that that is always implemented like that. In reality, of course, every software developer can do what they want. Yeah, I'm just suggesting an architecture and a design that I would use and feel like is very appropriate. So before going into that, maybe let's briefly recap this slide we looked at. So we looked at the different usages. We looked at the different layers in that stacked architecture, and somewhere in that layer there's a database system. And then depending on how you, what decision you make, whether you host your software stack completely in your backyard, like on premise, or you are somewhere in between. So maybe you even have platform as a service like here, and the database system is managed by some cloud provider. Technically, it doesn't matter that much in the sense how the database system is used by the application. It's just a decision where the database system resides and where those calls happen. So there's no difference about that. And we talked about the different pros and cons of these architectures, and there's not the single truth in that. It really depends on your workload, on your use case, and what you are willing to pay, and how much staff you have to manage these architectures. You should be very careful. That was one of my messages. And the second message was, you should design your software to be flexible, to eventually revisit your decision. If you made a decision to be on premise and then go to the cloud, you better have your architecture provide. And that's relatively easy if you wrap your layers into Docker containers and think about your design early on. And the third insight we had was really, this is an oversimplified graphic. So in reality, this may be different. It may actually be that one of those layers, say, whatever the operating system, for instance, consists of multiple operating systems, multiple file systems, even the distributed system. Actually, this week's assignment will look a little bit into that. And also later on in this lecture, we will see again, as last Wednesday, that this is just a conceptual view. How a layer is implemented may differ a lot, depending on what you do. So today, we look into the architecture. And here we go. Again, I start with slides a little bit. And so we do a lot of code today, actually, walking through the interfaces. But I will first go through the slides, and then we have a long coding session. So there's one literature I would recommend for designing is really design patterns. Did any of you already read that book? No. Okay, did you hear? Who heard about design patterns? Okay, that's good. So I think it's mentioned in one or the other courses, at least software engineering, I guess, and programming too. If there are like 5 books in computer science you should read, this is on that list, to my understanding. So this was really a game changer. It appeared in 1994. I think I bumped into it in 98 or something like that, and it really, really allows you to make much better software designs. And the book presents a list of reusable patterns, patterns you see in your software that reoccur over and over again. And if you're able to see these patterns, when you see a problem, you see, oh, that can be solved by that pattern, you make your life so much easier. It's super, super useful to know about these patterns. And don't be afraid to, if you see the long list of patterns, it's actually, maybe I only use 5 patterns of those, actually, and you can do 90% with those patterns. It's basically inheritance, adapter, wrapper, strategy, maybe facade or something like that. Maybe those 5, I don't know, factory, maybe 6 or 7. You're good to go. If you know these, you can solve most of the problems. So I highly recommend that. Yeah, so database architecture. So we will look at those questions. Which API does the database management system offer to users? Of course, there's a lot of legacy involved in that, as database systems were conceived in the 70s. People made decisions at some point, and those decisions are now carved in stone. Now, the best analogy still here is when you think about our railway system. Why does the rails have that distance? Because that corresponds to a horse carriage, basically, back then. And then based on the horse carriage width, they decided, okay, let's do something similar for the railway system. And then it's not carved in stone, but carved in iron. You start building those railway tracks, and that's very hard to change. If tomorrow you make a decision, oh, it would be so much better to have rails with 20 centimeters more. Yeah, good luck changing all the rails in Germany or Europe. I think Spain used to have a different rail system. Does anybody know whether that's still true? It's a bit wider, the track. At least in the 90s, when I traveled to Spain by train, they had to change the axis of the wagons to be able to ride on the Spanish train system. It was a bit wider. I'm not sure how it is nowadays. Yeah, but then you have these problems if you don't agree upon a common standard. Yeah, and the standard, of course, is SQL. The standard is you send a SQL command and you get results back, and that shapes the API of a database system a lot. So we will also look at what are the principal components of a database management system. Again, this may be different depending on your implementation. There were also proposals to standardize that. I am not convinced about these proposals. And actually, you see it in each and every database management system. Everyone takes different decisions. I take different decisions. I believe my decisions are the best, of course. Other developers believe that their decisions are the best. I mean, it's a typical effect you will see in software development anyway. Every software developer believes, yeah, I'm taking the best decisions, and whatever everybody else says is crap. Yeah, that's, you see, or sometimes meet these kind of people. It's not always, but yeah. Software development is full of people with strong opinions, let's phrase it like that. And I have a strong opinion of that, about database architecture as well. So what are the right abstractions? We will look into that. What are the right interfaces and APIs for components and the database system? And in particular, what should be the right interfaces and APIs? Yeah, so in industry, it's much more difficult to change these interfaces, but in research we are in this big playground, and we can ponder upon, hey, what if we started relational database systems today? What would be the right interface? Yeah? Or an easier thing to change is to say, okay, we keep all the old interfaces, but in addition to that, we add another function, another API, allowing you to access the database system, which has some advantages. Yeah? And I will show you some proposals along the lines. I mean, the game, the thing you have to be aware of is always here, we are on a layer, there are certain users, you defined an API for the database system, so the users have to live with that API. Yeah, they can use it or they stop using your system. Yeah, so they have to use your API, however you defined that. But it's really important to look at how the heck is this stuff used anyway. So what would be the best API from the point of view of the user? And is that the API I am providing as a database management system? Yeah, so that's an interesting question to look at. How is it used? And not say, not simply say, yeah, database systems have that API, so why should I even think about it? Yeah, please think about that, yeah, because you might solve real problems with that. Okay. Yeah, and why should we even worry about database architecture? And I really added these slides because I frequently run into discussions where I hear some of these myths. So there's a couple of myths, and they apply for software engineering in general and software development, but also in particular for database systems. So those are the 7 myths. Maybe there are more. I find very important. So what you sometimes hear in discussions or an attitude you feel like is that software design looks nice on paper. Yeah, so you use an entity relationship model or an UML diagram or whatever modeling technique, but doesn't really matter in software development. Yeah, sometimes hear that. So it's nasty. I draw something. I want to code something. Come on, why should I draw a diagram? UML is yeah. And it's the same in our undergrad course. People create tables and database systems without thinking about the model in the first place. Yeah? And that's wrong. Yeah? Again, all these age-old, Stone Age analogies apply. Yeah? Programming is putting one stone on top of each other. Computer science is designing a plan for the house. Yeah, you're the architect as a computer scientist. You should think about first where's the wall going to be placed, where's electricity going to go into the house. Yeah, how does my house fit into the environment and the neighborhoods and stuff like that? You have to make a plan. That is what computer science is about. Coding is about then, okay, I put this stone on top of each other. And you better code based on a plan. You can also code without a plan. Not sure whether, there's some houses in Saarland actually where you see, okay, the guy coded, put one stone on another without a plan. If you look carefully, you see that here in some streets. It's rare, but in most cases, of course, people use some sort of plan. Okay, so myth number 2 is I do not receive any benefit by thinking about the right design. This one. So if you feel like I just do design because, one should do it, there should be some sort of encapsulation. I don't know. No, because it is so, design, one main purpose of design is to hide information. The other purpose is also to make your architecture flexible, robust, and maintainable. And that also leads to extensibility. If eventually the customer comes in and says, hey, I also want to have that feature. If you have a good design, you hopefully can extend your software to support the feature easily. If you, with a good design, the likelihood is so much higher that you can do that. If it's just a bunch of spaghetti code, you're probably lost and won't be able to do that. And the third is I can still make any changes as needed later on. So that's basically the attitude, okay, I don't do the design now. I do it later. I can refactor it later. I just quickly hack it in now and then see where that goes. Myth number 4 is it's much more important to get the algorithms right than wasting time with useless design. So that's also more like an attitude of, okay, it's all about performance, algorithms, complexity, and stuff like that. In other words, so algorithms do not have anything to do with software design. No, that's true. Yes, even if you have small algorithms, they have to do a lot with software design. We will get there in a moment. Then what's also very frequent in systems, and in particular, so database systems, so there's a subtopic in computer science that's called systems. Yes, it's a couple of different research areas. So one is database systems, there's operating systems, there's file systems, networks. I hope I don't forget anything. It depends on how the people feel that they believe to the systems sub-area or not. But basically all research areas that deal with building systems rather than algorithms or smaller parts or doing theory. It's really about building the entire system, like in the database system, like in this lecture. And in those fields, you often feel like that people worry a lot about physical structure. So physical structures being would I use a hash table, would I use a B tree, binary search tree, would I use a bitmap, or whatever physical data structure. And we will see that this can lead to erroneous decisions. I will say a bit more about these myths in a couple of extra slides for a moment. Just here, it's just to mention the myth. So myth number 6 is it's much more important to leverage each and every low-level performance trick in the programming language. And 7 is design and abstraction always comes at the cost of performance. And guess what? All of these myths are dangerously wrong and stupid. So let's look at them in more detail. So this, for all of these myths, basically all the wisdom from software engineering applies. So pick a course, software engineering course of your choice. If you're not familiar with these things, I think it's super, super important to have a basic understanding of software engineering if you build any systems. If it's just about programming, you're wrong. You should know about design and basic software engineering. Basic, okay, what you mean by basic, but design patterns is so important. So all that wisdom also applies here. In the following, I'd like to make some database-specific comments about some of the myths. So one is about myth number 1. Software design looks nice on paper. Actually, there's a duality. Yeah? So the database people talk about data models like ERM, and software engineers in general talk about UML diagrams. You can actually also model data with UML. We typically don't do that because it's too much complexity for what we need to achieve. So I always stress in my undergrad lecture, entity relationship modeling is good enough for the database world. But you could also use UML for that part as well. But what you see is that you have similar problems and similar solutions in these worlds. Yeah? If you screw up your data model, you will have the same kind of problems as if you screwed up your software design. It's really the same problems that occur. Yeah? So that's why I always say here, data model / software architecture or software design, whatever. It means the same thing. It's really, I can always make the same sentences about both words. Yeah, so a well-designed data model or software architecture, they're crucial for maintainability, robustness, and overall impact on the system. Yes. So by impact, I mean here that you do something, and then the question is how much of the system is going to be changed if you do any change in the system. Any flaws in that data model or software design will spread and multiply throughout the code. What do I mean by that? Basically, you see that so often. Assume you build a data model and then you build a web application on top, say using Django, yeah? And you have a shitty data model design. Maybe you forgot about normalization, or you have really stupid columns and partitioning of tables and stuff like that. Once you have the model, application developers will start using the model. They will write queries against the model. They will write code against the model. So it's very difficult to get rid of the shitty design you started in the first place. Yeah? So basically, the application developers will start carving your shitty data model in stone by writing code. That will be very hard to change. There are tricks in database systems like views you can use for that. But in general, you will see that if you do something wrong in the data model, that will spread throughout the application. And the same happens if there's a missing abstraction in your software design. You will also see that in other parts of the software that will spread. Yeah? And it's very hard to get rid of that. So my recommendation in general here is that avoid compromising in data modeling and software design. And that's easy to say, but very hard to actually implement and get it right. So I would say you might do compromises here and there in software design to get stuff done. Yeah? In an ideal world, whenever you see a problem, you can refactor and redesign your entire software. But in a practical situation, that's not going to work. You have to make compromises somehow. You have to find the sweet spot, yeah? the right trade-off there. So you can't be 100% perfect. I think that will work. Yeah? But this compromise you should never do in data modeling. Yeah? You should never start hacking another attribute into that relation, polluting the semantics of relations, or introducing weird stuff in your data model. If you start doing that, it's over. Then the next weirdness comes in, and then the next, and the next, and the next, and eventually you ruin your data model. So my message is you should be much more careful on this, on the data modeling side, than software design side. Yeah, and any ugliness in your data model and software design will spread and multiply throughout the code. Yeah, it's the same as with flaws. Actually, I could put these two sentences together, right? I think it was so important I had another bullet point. I think there's a bullet point 6 that repeats it again, and 7 again says the same thing. Yeah? So the stuff is spreading throughout your architecture. Okay. The art of making excuses. So core myth number 4, it's much more important to get the algorithms right than wasting time with useless design. And the interesting insight here is that when you design algorithms and work with algorithms, often algorithms in particular in papers come with, yeah, there's a bunch of code, there's a couple, whatever, 30 lines of code. Yeah? But when you analyze that in more detail, you often find that you can throw design patterns at that. One pattern is a strategy pattern, for instance, that you can use often in algorithms, a strategy determining how a specific subset of the algorithm is being implemented. Yeah? If that is factored out in a strategy pattern, you're good to go. And you see that everywhere. So you should not separate developing algorithms from software design. Software design goes as fine granular as designing algorithms. So it's very important. Yeah? And another recommendation I can make here is every friction point in your design, take it as an opportunity to improve your design. So what happens frequently in software is that I forgot that, I should change that. Yeah? And often when you feel like, okay, I can now add a parameter, but actually I should redesign my class hierarchy, then go for the latter, go for the class hierarchy. Try to get it clean, try to get it right. Don't start hacking stuff into your software. It's always an opportunity to make things much better. Yeah? Because then you may end up with better, more general, more flexible, and maybe even faster algorithms or new algorithms. Yeah. And number 4 is getting algorithms right. Yeah, whatever that means to you, is exactly about understanding their core properties and different aspects and how they interact with one another. That's basically, in different words, what I said before. So often you see algorithms as like, there's a bunch of code, maybe there's 100 lines of code that's the algorithm. Yeah, but the art is then to dissect it, to break it up into components and to understand, it's actually it can be broken up into this component and that component, and sometimes this is called, sometimes that is called, and the component can be exchanged, tra-la-la-la-la-la-la-la. And if you're able to do that, then you can analyze the algorithm much better, and that often leads also to performance improvements. If you feel like, hey, wow, I can now exchange the component. Before it was just 7 lines of code that somehow interacted without a clear interface with a context, but now I can exchange that. Yeah, and that's a super great opportunity. Yeah, maybe you bumped into this sentence, so premature optimization is the root of all evil. Yeah? And that's also something I'm following in this lecture, as for the moment, we are still looking at the very conceptual level of database design and how database management system should be designed and how it works. I don't look so much into the physical things. I don't look into optimization aspects because it's on a different axis, a different dimension. This is the spaghetti analogy I showed to you at the beginning of the semester. Yeah, and that's again the same thing. So I think the art, and that's hard to learn in a way. Yeah? So because, you're trained in so many lectures to, hey, it should be efficient, complexity should be super great, and it should scale like crazy. And there you can quickly take the wrong turn by optimizing your algorithm too early, too quickly. Yeah, it's the art is to stay on a certain abstract level for a moment and say, okay, I solved this problem in principle, that's my algorithm, it's absolutely stupid, but hey, it works. Yeah? Think about in the database world, for instance, there's join algorithms. Yeah? You should remember from the undergrad lecture. If you have this join predicate, you can implement every join algorithm in the world through a cross product. Yeah, cross product. Yeah. Every tuple from the left input is combined with every tuple from the right input. You do that, you have the size of that is square, number of tuples from that times number of tuples from that. Yeah? And then you apply the join predicates through a selection. Yeah? Then basically you inspect each of those tuples created by the cross product, whether the tuple qualifies. Has square complexity, you don't want to use that, there are better algorithms, but hey, it works. It works. Yeah? It's enough to do testing, to prove a point, to have some results in your system. Yeah? You shouldn't forget to get rid of this square complexity, yeah? Make a big to-do in your code. But it's a start. Start with a stupid algorithm and then try to build something better. Yeah? Okay. Yeah, it's number 5. It's much more important to get the physical structures right. Yeah, and that's also, you see that, in particular in database people, and also in my group, we do the same, makes the same discussions. Yeah. So the effects of using the latest super duper index structure or any other data structure are overrated. Yeah? So you can make a better index, you can make a better data structure, and you can generate graphs where that index structure is better in super duper high performance scenarios, but nowhere else. Yeah, that's a big takeaway we had also in my group in the past 10 years. Yeah, you can always be better, be more efficient, but in a general usage of a database system, you won't feel this stuff. It's not going to be there. A good, any binary search tree, B tree, hash table will be more than enough to serve your workload. Yeah? And the same is true for so-called data layouts. We will briefly visit that later on. Did anyone hear of you about column store, column layout already? Row layout? No? Okay, we will get there. I will explain that, what that means, yeah? But it's a similar discussion you should be aware of when thinking about database systems. We look at that in more detail. We have a notebook on that already where we show that. Yeah, and again, it's a trade of complexity and performance. Yeah, so do you want to have that complexity by having a super duper physical structure, super duper index, which does all kinds of tricks? Or do you want to have something simple that actually works? Maybe it's not the best performance you get, but it's good enough for your purpose. And that's a very important design decision you should be aware of. And the same holds for data layouts as well. So that's also something we look at in the next weeks. So for the moment, what you learned in this class so far, I never looked at how to persist data on the file system. Yeah? We touched that briefly today, but we basically kept everything in main memory in dictionaries in Python. But of course, in a real system, eventually you want to persist your stuff somewhere on storage. Yeah? And then you have to worry about how would you do that. And there are certain scenarios where you can really be much better than doing it blindly. Yeah? And we will look at that. One is compression of data, the other is data layouts. Yeah, myth number 6 and 7, it's much more important to leverage each and every low-level performance trick in the programming language. And 7 is design and abstraction always come at the cost of performance. And both are wrong in most cases as well. So fiddling with every bit, yeah, you see that sometimes with very experienced programmers. I really want to get everything from the machine. I do some bit shifting and tra-la-la-la-la. That's nice. That's maybe an important goal for certain high-performance scenarios. But you should never do this at the cost of maintainability, robustness, and software design. That's a bad trade you're doing. Yeah, if you are really even if you are in a situation where your boss is in your neck and says, yeah, it has to be super, super duper fast. I mean, why would you sacrifice design because the next week your boss comes in and says, hey, I also want to do this requirement. Can you do that? And then you're screwed because you messed up with your design. Yeah, you should always be sure to, I can still change it. If a fancy design comes in, if a fancy requirement comes in from my customer, can I still adapt my software? Or am I just 1,000 lines of spaghetti and there's no way of ever changing that? So I think it's rare that you should, that you should sacrifice. No, you shouldn't sacrifice design, software design. Maybe that's the answer. Yeah, and what you see in software development is also, so we also ran into that trap multiple times. For instance, I think 10 years ago, we had we implemented some database system and we wanted to make it super efficient. And then we bought a book on C++ templates. Yeah? With templates in C++, you can do all kinds of magic. You can nest them like crazy. Did you ever use templates in C++ like that? Yeah, you still feel the pain, kind of, a little bit. Yeah, someone used templates without feeling pain. No? Okay, good. Thanks for not ruining my lecture. So, but the output of the errors it's not so easy. Maybe now with ChatGPT, you put it to ChatGPT, the output, the error of the C++ compiler, and maybe then you can fix it. But it was really hard. Yeah. So in terms of getting things done, yeah, making sure some functionality is developed there was a bad trade. Because I saw in the team that the trade-off was like, so people were fiddling with template magic, trying to understand why it would work on this compiler and not on the other, and why in this situation it wouldn't work and there it would, yeah? Even though those were very experienced C++ developers. Yeah? So just don't do it. And the same holds for code reviews. Yeah? I also saw that in one project. So of course it's important to show off. You can also do that in Python. I use the latest Python whatever feature in the language and combine all of that, and then it's all super compact. Yeah? But there's a price to that, because code should be accessible by everybody else in the team. Or at least if you're working on the backend people should be able to read it. Yeah? And of course you can expect that those people learn a bit about the latest features of the programming language. But if it's super magic, convoluted, maybe in C++ another example would be bit magic, shifting back and forth, ending, oring, maybe even without having any command, explaining what the heck's going on. Yeah, that's a problem for your software team, because then it's not accessible. So from a point of view of a software team, it's much more important to have easily accessible code, readable and understandable by many developers. Yeah? I look at the code and I quickly understand what the heck is going on. So what the code actually does. So. Yeah, high performance scenarios are rare and overrated in database research. I mean, it's fun to look at that and you can squeeze out a lot, but in the general case, you don't need this stuff. Huh? And still, often it's possible to have both an awesome design and awesome performance. Yeah? So we look more at that in this lecture. We touched on that briefly in the undergrad lecture, but databases already do that. You have an awesome design, you have a declarative query language SQL. You don't have to worry, how the heck do I run my SQL statement? The database system will do all the magic. It will actually translate SQL into executable code, into a binary that is super fast, that looks at how the data distribution is, which physical structures are available. You don't have to worry about all of that. Yeah? So even though you're very abstract and declarative, you got awesome performance. And that performance is hard to beat with a handwritten piece of code. So actually, those two things, abstraction and design and high performance, doesn't have to be a contradiction. That's important. Okay, so maybe before looking into now let's look a little bit in the code. So basically, this is now enlarging this database layer. And basically, for all of these layers, of course, in the graph there's an API. And that is what you can use. That is what you can call. That is what this arrow is about. You call certain functions. The application calls certain functions. Or it could be the Django ORM sending SQL in that case and receiving result sets for further processing. And inside the database management system, there are further components. So for the moment, I'm not showing all of them components. Throughout this course, I will add more components to that. Yeah, this is what we had so far. And this is how I would assemble those components, how I would use those components inside a database management system. And one thing we touched upon briefly last time was this persistence layer, or basically think about this as an operating, as a file system. So the database system, eventually has to store the stuff somewhere. Yeah? So that's stored on a file system. For instance, it can also be an object store. And you see here, I already broke it up into two parts. Yeah? And so here this layer consists of possibly two different stores. I could actually use the same store, but I could break it in two different stores. And what this means is our MVCC store uses a different persistence layer. So this MVCC store has one persistence layer, and this and the entire system has a link, has a handle to another persistence layer. This may be useful for query processing. So you process a query, and while processing the query, you will access the store, of course, and ask for this object ID and the other object ID and filter out stuff and join stuff. But that's done outside the store, basically. But for temporary data, for instance, temporary results created during query processing, you could use this additional persistence layer to store. It could again be a file system, could actually be the same file system, could actually be a separate directory in that same file system. That's fine. You could say, I mean, the easiest configuration here would be, yeah, so this is a directory on your file system used for persisting data from the store. And this is a different directory on the same file system used to store temporary data. It could even be /temp. But I'm just conceptually, I'm splitting it up and I'm saying it's kind of two persistence layers, and you can make it different SSDs, different servers, different storage systems, whatnot, up to you. Yeah? Okay. Yeah, what's striking here already, you see a couple of key value stores. Yeah? You see that a key value store, so the persistence layer I'm modeling as a key value store. In both cases, recall how I introduced key value stores in this lecture. I said, well, a key value store, you can represent everything. You can represent the file system. Yeah? The file system path maps to the binary contents. That's the key value store. Yeah? Or you have an object store. The object ID maps to the object. That's what we used in MVCC. Yeah, that's the same thing. That's an object store. Yeah? So it doesn't matter. It's some key value store. You may call it file system or object store as you wish. And then we have this key value store here. That's how we started. This is a non-transactional key value store I started with. Yeah? The store that keeps versions of committed tuples, committed versions, plus this one work in progress version. But that's totally non-transactional. Yeah? You can ruin your consistency like crazy with that. And then in the next lecture, we extended that through inheritance to say, aha, I have this MVCC store, which inherits from the key value store, adding asset properties. A and I were added. Atomicity and isolation were added. Consistency is orthogonal. Durability, well, not sure what to do about durability. Yeah? It's still kind of open. As said, we will handle that later. But maybe that's a good point in time to discuss a little bit the D. The durability. So what do you think? How would you even guarantee durability in such an architecture? So durability, again, meaning when the transaction commits, the database system has to guarantee that it never loses the changes you made. You did an update to some object and begin transaction, update, commit transaction, the call returned, the database system said, yeah, I committed that. And then the contract with the database system is it must never, ever lose that data again. So how would you do that? Any ideas? The same just happened maybe if you watched carefully. I changed the setting in PyCharm. Then PyCharm went nuts. I killed the process. I started PyCharm, and PyCharm didn't have the setting anymore. I had to re-enter the same setting because the setting was not persisted on disk. Yeah? Same happens for database system. You change something, you change a tuple, you change it in memory. What does that help? I mean, you kill the process and the change is gone, right? I mean, you better have it persisted somewhere. So how would you even do that? Yeah?
Maybe ensure that persistence is managed in a different process.
Mm-hmm. Well, how exactly would you do that?
Create a child process that manages it.
Mm-hmm. Yeah, but still, in the process that performs the update, you still have then to trigger that process to actually also write it. Yeah? Because, I mean, if you think about the implications, you must not return, the commit call must not return unless the data was persisted. You can't defer the writing the data to some persistent layer Yeah, you can't say, okay, I first return, it's committed, while it's only in main memory. That's not possible because it's not durable. If you don't store it somehow, you return the commit call and then the process gets killed. The data is lost. Now the data changed you made is lost. Yeah? Do you see that problem? Yeah, main memory is not persistent. Yeah, you switch off electricity or there's a software error. Yeah, you made all kinds of changes, but then the process is killed. All changes you did to the database are gone. They're not there anymore. And that violates the D in ACID. D saying durability. If the commit call returns, the data must be durable. The data must have been stored somewhere such that if you if you restart the database system, you get back to the changes. Yeah, that's the contract of D. So how would you do that? What are your options here? Yeah?
Usually it's done by write-ahead logs.
Mm-hmm.
You write what you're going to do next, and then you go do it, remove the log, and then return to the user.
Okay, so you read about, you knew a little bit about databases before. That's done through a log. So a log is basically, so remember a pirate ship, and the captain has a logbook. So every day the captain wrote in the logbook, oh, today we raided another ship and we found like 100 kilograms of gold and we killed 10 other people. And the next day he writes in the book, oh, we saw a whale but we couldn't kill it, stuff like that. And the next day he says, oh, we almost sank in the storm. Yeah, that's a logbook. And the database system, almost all database systems do the same thing. They log the actions, they log the changes that were done in that logbook. Okay? So what if the ship sinks and the logbook is sinks to the ground of the sea, like 10,000 meters feet? So is the change you made still durable? You say yes? Why?
You said the logbook is?
Yeah, we write a logbook. Let's say we do the same pirate ship idea here. We write a logbook. Every time you do an update, you write it in your logbook. Oh, I updated object ID to be this new value. I deleted object ID 42. Oh, I did this and that. Every time you do that, you write it in the log. And once you wrote it in the log, only then you return the call to update. That's what's called write-ahead logging. So what we do is we first write the entry in the log, and then we return the call. Now what happens? What happens if the ship actually sinks and the logbook is lost in the sea somewhere, like 10 kilometers below the surface? So is it still durable, our changes?
Not anymore.
Not anymore? Any other opinions? So he says not anymore. Anybody else? Would someone claim it's still durable? Or changes protocoled in the logbook? Is that durable or not? Yeah? Yeah, very good point. So, okay, maybe the log is waterproof, a special pen, these kind of things exist. So let's assume for the moment the logbook is still there, it's not dissolving in the salt water, it's just on the ground of the sea. Yeah, but not accessible to me, but it's still there. So are the changes still durable, yes or no? Yeah. If you go there, find the log, you can use it, and then it's still durable. So if you get access to the logbook, it's still durable. Yeah, I don't know, when was it when the pirates were active? Back then, maybe, I don't know, 400 or 500 years ago or something like that. So I guess they didn't have the means to go down 10 kilometers under the sea surface and recover the logbook. So from that point of view, for them, it wasn't durable. So let's assume the book is built based on a material that doesn't dissolve over 500 years. Now we could go down there with a submarine, recover the log, And from our point of view, it's still durable, right? Yeah. So durable is a bad term. Or it's a not bad, but it's a misleading term because durable is in the eye of the person. It may be durable to you, but not to me. A good example is also, my favorite example is still Star Wars. I also mentioned that in the undergrad lecture when this Death Star destroys a planet. Yeah, so all the databases on that planet, all the administrators and all professors claimed, that was durable. Yeah, I wrote it to media, I was persisted, I even had 5 copies on my different disks. Yeah, but then Darth Vader comes in, destroys the star. So is the data durable or is it not durable? What do you think?
I mean, if there were redundancies on other planets.
Louder, what?
If they had redundancies on other planets.
Yes, if they had redundancies on other planets which were not destroyed by Darth Vader, then the data is still durable. Yeah, but if all your copies were on the planet, no, the data is not durable anymore. Even though the database system before on that planet said, I could commit it, I made it durable. Now all of a sudden durability is gone. Yeah, so durability is a very difficult term. It's really in the eye of there's no perfect durability. You can't achieve that in this universe. As far as I understand physics. Yeah, so there's always can be another copy, but if all of the copies are destroyed, so what? The data is not durable anymore. And that makes it a bit difficult. Yeah. Okay, what other things, if you think about our cloud architecture, so, I mean, when do you make it durable? That's also something you will discuss in this week's assignment. But basically, what will happen is, in some point, when you make an update, in one way or the other, when you update something and commit your transaction, the database system has to persist the data in one way or the other. There are many ways of doing that, but somehow you have to do that, which means you make a call to the underlying persistence layer here. Yeah? So in this case, it can be both of them actually, or even a third one, but you persist it somehow to the layer. So what will go wrong? What can go wrong? And that's the problem of abstraction actually. Yeah, so the database management system says, okay, hey, persistence layer, hey, file system, I have a couple of changes. I want to make sure you really put it on some storage medium like this one, which persists it and can survive a power failure. An SSD or hard disk or tape or something like that. Here's the data, make sure that's persisted. Save those changes. Or you open a file, you write some data to the file, you close the file. Everything good or everything, what can go wrong? Yeah?
Technically, there could be some kind of transmission error where the message is sent and it's received.
Yes, right. That could happen. Some transmission error, something goes wrong while writing. Hopefully you catch the error and try again or something like that, or at least, so if the database system catches it, it could then say, oh, I'm not committing the transaction because I'm not able to write it. That would be one way of handling that. That's right. What else could happen if you write to the persistence layer? Did you ever use file system handling in any programming language? Python, it's this pickle interface, or C++ with these streams and these operator logic, the streaming I/O stream stuff. Yeah, you write something to a file. I guess you used it somewhere, right? But what may happen? And why is that a problem of the abstraction we're using? So again, the persistence layer has some sort of interface, our key value interface, right? But what can go wrong? Other than errors, yeah, sure, okay. But let's assume it works as intended. What can go wrong? No idea? Never had that? Yeah?
Many things could go wrong.
That's a great answer. That's always the right answer. Okay.
Like starting from file system failure, from device failure, or
Yeah.
even worse, two people might like update the same file and then the last change is gone, or
So similar as in a database system, write-write conflict.
many things.
Yes.
Or you might be in the middle of writing a transaction, you
Mhm.
write some of it and then you crash, so you are in an inconsistent state because
Yeah, again, then, okay, those transactional logic should be handled in MVCC. If there's any error from the file system, the MVCC store should say, no, I'm not committing the transaction. So you would catch that, actually. Yeah. Okay, that's all right, but I'm trying to allude to, so what do you expect when you write a file to a file system? What is your expectation? Yeah.
You
That-
can retrieve it again.
I can retrieve it again. That's true. Okay. Any other expectation? Yes.
Operations could be performed on it.
Operations?
Could be performed on it.
Yeah, true. Yeah. What else? What is your expectation when you write a file to the file system? When you write a file, write. Yeah.
If you won't lose the data,
What?
if you will not lose the data for the future reference.
You will not lose the data. What does it mean in terms of an SSD?
Like in the sense, if you need it, if you need to perform particular actions, then you will be able to,
Yeah, that's true. That's, I mean, basically, I wrote it, I stored it on the file system, and now I should be able to retrieve it in the future. Like that's durability contract we just talked about, basically. Yeah, so it's not lost. But what I told you before is, so I made the difference between RAM, DRAM, electricity is gone, data is lost, versus SSD, electricity is gone, data is still there. Yeah, so the data is actually written on the SSD. But what does it mean for writing to the persistence layer? And in particular for file systems, this is true and a problem. Yeah.
There is enough memory.
Yeah, there could be enough memory. But what happens when you write a file? Is it forced to the storage medium? Never bumped into this issue? It's not. You write a file, the file system would say, yeah, I wrote it, yeah, nice. Actually, it's just the main memory, just buffered somewhere. The same holds for almost all storage devices. All of these devices, not all, but most of them have some sort of RAM, the type of memory that will be lost once electricity is gone. Writes are typically buffered and not directly written to the storage medium. Now, if your idea of writing is, I write it to the persistence layer tells you, yeah, I wrote it, twinkle, twinkle, but it didn't write it, but just does it later, then you're screwed. Because then on the database system, you believe, I made it durable, I wrote it on the file system, and the file system lied to you, said, yeah, so eventually I wrote it, yeah, for you it's okay, I wrote it. It did not. Power failure, change is lost. Yeah? And that is why you have to be very careful in a database system to force those writes onto the storage mediums. The method always has the same name. It's called flush. Yeah? You like flushing a toilet, actually. So you flush your changes, you flush your writes to the storage medium. And when implementing the database system, you have to be careful to actually call that method. We will see that later on in our implementation. So there's a flush method in the key value store that we should be able to call, and actually extended our key value store from our implementation a little bit along the lines. So this is now the API of the key value store. And I think we talked about size and put and these kind of methods. as a get method, so you get an object ID and get the object that's associated with that. You can delete something. I think that's a relatively new method I added. But then there's a flush method. So the flush method, if you, question? The flush method allowing you to either flush everything. If you set this object ID to none, this means, okay, whatever changes you may have in main memory that were not persisted yet to the underlying persistence layer, now it's the time to flush. And that method will only return once that has happened. Yeah? It must not be deferred or different process or something like that. Yeah? It must do it really synchronously, and once everything was flushed and forced to the persistence layer, to the persistence medium, then that method is allowed to return. It's also useful to have a parameter that says, okay, I only care about this object ID. Make sure this is flushed. If the others are not flushed, I don't care. Yeah, from the point of view of a transaction, of course, if you want to make sure that the changes done by the transaction are flushed before committing, then you can call the flush method for each and every object ID changed by that transaction. You don't have to flush everything in the store, just the object IDs you want to persist are important. I think the other methods are still the same. So you see it in the code. I mean, so this code is, I'm working on the code, extending it and improving it every week. So you should maybe pull again from main if you don't see these changes currently. Okay, I know this. Here we go. And here's again a summary of the roles of these different stores, but basically explained that already. So we have two different key value stores here being used underneath. One is one is used exclusively by the MVCC store. The other is used by the system for other stuff. For instance, temporary data and query processing. Then there's the key value store that we used as a foundation for MVCC. We extended it through inheritance, and our MVCC store is a key value store, extending it to add transactional functionality. And the MVCC store, of course, is a fully transactional store with respect to A and I, but not really D yet. Yeah? So D is not implemented. There are different ways of doing that. I think we'll spend a separate lecture on that. Okay. So I can still show this one. So this is a UML that I generated from the code. It's kind of reverse engineering. Yeah? Of course, the UML should come first, and based on that, you build the code. But of course, you can always write code, generate the UML, and then claim, yeah, I did software design initially, right? That's my software design, yeah? And I didn't do it after the fact. Don't do this, yeah? But I'm not sure if, I think you can basically go, I have changed presentation mode, not sure whether I have access to that, but basically you can go to store and then diagrams, show diagram. And then you get this UML generated automatically. Yeah? Helps you to understand if you get lost in your own code, that's something you can do. And that's the same thing I did here, actually. What's a bit unfortunate, though, in PyCharm, and that's a known error, and they haven't fixed so far, is that the arrows go in the wrong direction. So typically, the arrow should point up. Yeah, so if this is a user, this is extending. This one is extending this one. However, the arrow goes down here, which is super weird, I would claim. That should be the other way around. The arrow should be here and not there, to my understanding. Maybe some UML dialect defines it like that, I don't know, but I find it super weird. So in particular, in anti-relationship modeling, we do the arrow the other way around. Anyway, it helps to get some understanding on, that's my overall design, if you like these kind of diagrams. Personally, I don't look at this stuff too often. I rather read the code and build the diagram in my head. Okay, so before we go into this one, so the individual components, I would first make a little tour to the outer interface. Yeah? I mean, these things are intertwined. What are the inner components and what is the outer interface of the DBMS? But let's start from the outside. So how is the database system actually used by any users and what kind of interfaces are available for the database system. And in the code you see we now have, where is it? Here, class by DBMS. Okay. So that's basically the Python implementation of a database management system. And that corresponds one-to-one to what I saw displayed on the slide. Yeah? So I have a class here that extends database management system. And so we can directly look at this one. So that's the interface. There's this weird Python notation for abstract classes called ABC, abstract base class. Yeah, so it's not a keyword in the language like in Java or something. It's you extend ABC and then it's abstract, whatever. Yeah, and I'm also inheriting here from the asset store and a queryable component. And recall, when you inherit from something, you must be able to say is a. So a database management system is an asset store. A database management system is a queryable component, whatever that means. Yeah, but it's very important. Yeah, so whatever, if you say like if you had like a standard generalization architecture on object orientation, you have a vehicle, planes. Yeah, for instance, plane is the abstract base class, and you have whatever, a jet plane is a plane. Yeah, or whatever. What other planes exist? Propeller, turboprop plane is a plane. Yeah? So you have to be able, in your natural language, to say is a. If you can't say is a in language, then the modeling is wrong. I think that's a good trick here. So I get handles to those components. Yeah? That's the components. I just maybe can go back here to this slide here. So we had these components: query optimizer, MVCC store, and the persistence layer. So when I want to initialize the database management system, I have to pass handles to these components, which are initialized outside of the system. And that happens here. So I have this asset store that I'm passing as a reference. That will be my MVCC store plus some extra functionality. I have my persistence layer, which is a key value store. And I have a query optimizer, whatever that is. We will look into that later. But that's basically the things I need. And again, the second persistence layer can be used outside and can be passed to this asset store, as shown on the slides. Yeah? So the asset store has a handle to a persistence layer. But that is passed to this store when I initialize the MVCC store. Again, this can be the same handle. Yeah? If you don't create conflicts by that and write to the exact same files and directories. Yeah, but in theory it can be the same underlying device. Yeah. So that's how you initialize a database management system. So let's look at the interfaces that are provided. So one is asset store. I factored that out. Yeah. So when I think when I explained MVCC in this lecture a couple of weeks ago, there was no interface for that. MVCC is one example how to get an asset store. There are other techniques for that, like two-phase locking, see undergrad lecture, tons of different MVCC variants, whatever algorithm you want to use. You just want to have an asset store. MVCC is just one example for that. So I factored the functionality out into an interface. Okay, there's a constructor, the persistence layer I just mentioned. There is all the methods we already learned about in the MVCC store. Yeah? So commit transaction, abort transaction, update object, delete object, that's it. So all those methods we learned already about when talking about MVCC. And now the code changed, of course. Now I have, where's my DBMS? Oh, no, I called it transactional key value store. It was a rename to have a better name here. So that basically now inherits there and inherits from the version key value store. So the key value store is a non-transactional store that allows for these lists of committed versions. Yeah? So I inherit from that, and then based on that I build yeah, I built all the bells and whistles I need for the store. Anything else I can, that's the MVCC store we basically learned about in previous lectures. Okay, so let's go back. So what is the DBMS? DBMS interface, we have this asset store interface, plus we also have a queryable component interface. So this is also called a decorator or wrapper design pattern. So the database system, maybe we go back again to the here. So the database management system has as a component a store, and at the same time I also expose the same interface as part of the database management system itself. So from the point of view of a user, it looks the same, whether the user would talk to the database management system or to this store is the same thing. It's the exact same methods. So I'm wrapping the underlying MVCC store. And the idea of that is to enrich the functionality. So what the database management system does from a high level is, yeah, it looks like an MVCC store, but it enriches your experience by adding a query optimizer. Yeah, by being able to optimize access to the store. The kind of access we had when talking about MVCC was absolutely stupid. Yeah? When we looked through the store, when we read stuff from the store, we would loop over all entries in the store. That's very inefficient. You don't want to do this. Yeah? You want to do something smart. And the smartness comes into databases through the query optimizer and also through indexes. We didn't talk about these things yet. But from the design pattern point of view is that I'm enriching the store to the outside by putting inside here other functionality you don't have to be aware of. As a user, you don't see that because you see the same interface. Yeah? And that's the idea of this decorator pattern. And the second thing that happens is that I enrich the interface. And this is done by what I call a queryable component. And that gives you methods you should have seen when using a database system. Yeah, so for instance, this is executing a query. So what do you want to do with a database system? You send a string, a query. And that should be part of a transaction. It doesn't have to be part of a transaction. If you make it outside a transaction, it's considered a mini transaction and executed directly. But as we discussed it in the MVCC part of this lecture, typically each execution of each query should be bound to a specific transaction ID. And that's what I'm passing here to the method. And that's a query string. That's all you need. And then the return is an iterator of objects. Yeah? Objects can be tuples, can be anything else. Yeah? Before I go on to why is it deprecated, so any thoughts on that? Any surprises? Yeah? Everybody knows about SQL injection and preparing queries? If not, watch the video. It's super important. It's the biggest security problem with databases, and that is the reason why you should never use this method. It's here for legacy reasons. All database systems offer this stuff, but it should actually be removed from the interface because it's such a problem. And like every week you have some data leakage from some company X based on this method.
Is it like SQL injection?
It's SQL injection, SQL injection, that's what I mean. I have it in a video if you want. It's from the previous lecture. It's in English. I explain it in detail how it works and how to avoid it. So the way to avoid it is that to split the query string to have two different parameters, the query and the parameters in a separate parameter. Watch the video if you explain it in detail. Yeah, that's a different story. It's not what this lecture is about. So don't use it. Yeah? Don't use it. It's just for completeness, and because we would see all interfaces and databases still have that method. Yeah? But the interesting thing is here is a string, right? I mean, what can we say about the string? Why is that interesting? Yeah?
Then it's not optimized, or because,
No, that's not what I mean. Or what do you mean by not optimized?
well, if you optimize it, then I would expect something other than a string, because a string is usually what the user has provided us. But
Yeah, but that's the outside interface of the store, right? So the user provides a SQL string. And so you have to pass it to the database system, and that's the point in time where it is passed to the database system. Yeah, so I can't do anything about it because the database systems were meant to be like that users send SQL strings and return some stuff, return iterators over tuples. So there I can't do anything about it. But what else is surprising, or what else comes to your mind if you read that maybe?
The line can be,
Please raise your hand always before, okay? Yeah?
the line can be like at any length, so there's no limit. You know how much.
Speak louder, please.
What I think is that since it's string, anything can be put into it.
Yes.
From the SQL thing and SQL injection, and then
Yes.
also the letter that is not in the UTs, that's not valid basically, and also.
Yes. Okay, so 2 messages so far. What you said, anything can be put in, doesn't have to be valid, right? That's the summary of what you said? Yeah, okay, good. Let's put in anything, yeah? Or let's put in whatever, let's say English. Is that a type? I'm not sure. Some English text. What about that one? The type is not defined, okay, sure. But if you defined the type and then said, okay, my database system, hey database system, give me some, I want to have this row professors and join it with lectures and give me every professor where the first letter is D. Does it make sense? Doesn't it make sense? Why not have an English language interface? So you could also make it English text or make it audio, right? I mean, you just talk to your database system. Hey, PyDBMS, not hey Siri, but hey PyDBMS, give me all tra-la-la-la. Does it make sense or doesn't it make sense? Yeah?
Maybe it should be an abstract syntax tree, because that's how we know it's not just an English text, but like lines of code.
Abstract syntax tree of what?
SQL.
Yeah, you could do, but why not an abstract syntax tree of English? Does that exist? I guess there's something like that in natural language as well, right?
Well, we want to use SQL, right? Not English.
You tell me, do we want to use SQL or not? Yeah, I mean, there's how I wrote this before. There's so many dimensions here you can discuss, and that's why modeling is so crazy important. Yeah? Of course, you could say string. Of course, you could say I name this parameter SQL query. Is technically anything forcing me into pass a SQL query here? No, it's a string, whatever I can pass. Okay, and then there comes semantic analysis as part of parsing the string, and maybe my parser only speaks SQL, and the parser will know that's not SQL, I can't do anything with that. But from the point of view of the outer interface, why would I restrict it? Yeah, I could say, okay, that's my, oopsie, no, I don't want to have string. That's my query. And that's a string. And if you just say string, this can be anything. Any natural language, text, and all kinds of languages and writings of the world can be passed here. Any string, even a computer program, anything can be passed here. So from the point of view of, so you can leave it like that, or you make a decision. Yeah? If you want to make the component only support SQL, Yeah, maybe we can restrict it here on the interface level and say that's a string that's valid SQL. Then you could parse it outside and check whether it's a valid SQL, or you still have to do it anyway internally again for security reasons. Yeah, but that's one way you can do. And the other implication here is it doesn't have to be SQL. I mean, it can be whatever, some other query languages. Yeah, there are other query languages out there, XParse, XQuery, and whatnot, many others. It's the same interface in spirit. Yeah? There's no difference. From what happens, you pass in some information and you get some data out. Yeah? So that's one thing that you can make a decision about. Yeah? In the code, I just said it's a string. It's whatever query. Yeah? And again, on the type, you could say it's an audio. Or it's a natural language. What about that one? What about querying the system with natural language? Any thoughts about that? Like Siri or Alexa, how they are named, these AIs. Does it make sense? Hey Siri, give me persons joined with, yeah? Mm-hmm. That's true, so it may be ambiguous, not totally clear what you mean with all natural language. Yeah, so, but hey, the system could ask back, hey, do you mean this, do you mean that? Or it could say, okay, I would translate what you said to a SQL query like that. Is that what you mean? Yeah, that will fix it. Yeah. Any other ideas on why that will make sense? Yeah. Yes, that's true. So I have to have the machinery inside to digest the stuff through a large language model. Yeah? And the large language model should then translate that, for instance, to SQL, which I can digest with my existing database system. That's true. All of this already exists. All of this is already done. Even chat, all these popular LLMs can do these kind of things partially, but they are specialized LLMs that allow you to give natural language, and then it spills out SQL. It already exists. Yeah. Of course, there are errors as in all of these LLMs, but yeah, it's getting better and better over time, so things are happening. Should we make that even wilder? What if I specify an image? So whatever JPEG image. Yeah, might not have text in it. It could just be an image of whatever, an elephant or something like that, whatever. What could that mean? Have you seen something like that? Yeah?
I guess it means that this function should validate whatever it takes.
Should validate what it takes as input. Yeah, okay, that could be the same thing. Yeah, so I'm alluding to, so if you don't restrict your types, yeah, you better validate it inside the function before continuing. Yeah? If this is text and SQL, and you pass in any string, you better make sure that that's really is SQL and not some other crap, yeah, that you can't execute. Yeah, you have to check it inside the system. That's correct. But assume I provided a query method like that, where I do not pass a string, whether it's SQL or another query language, but an image. What could that mean? What could be the use of something like that? And where did you use that before? Yes?
Reverse image search.
Reverse?
Like reverse image search.
Reverse image search?
Yeah.
Yes. Right, image search. Yeah? So like on Google Image, yeah, you have some image, you want to find out who the heck made that image. Is there a copyright issue or something like that? Yeah, that's the same. Yeah, you're querying for the image. Yeah? And there are tons of work in database literature where you query a database not by text, not by SQL, but by an image. Yeah? Give me all similar images. Or this JSON is the same example. Yeah? So you put here, is it pronounced JSON? I don't know. Yeah, you put up there's some music playing, you hold your, you start your app, and then the app looks up with the audio, there's some magic returning you the title of that audio. Yeah? So my message is try to see the query interface in a more general way. Yeah? For legacy reasons, it's typically discussed along the lines of, yeah, it's a text and that's SQL. Yeah, but in principle, querying a system can be so many other things. Can be audio, video, you name it, whatever. Yeah? Or for bioinformatics, yeah, the query might be not something you can express in SQL, but might be whatever molecule. Give me all molecules that are similar to this one. Yeah? That's called a similarity query. Give me all similar videos, give me similar audio, give me similar molecules, similar whatnot. Yeah? Okay, good. So, cover this one. Yeah.
But
Yeah.
is it necessarily part of the database, the DBMS? Because after all, there could be some transformer along the way, and then transforming to something.
Yes.
Yeah.
That's true, very good. So you can, that's obviously, that's a design decision. So he's asking, does it have to be part of the database system? You can do that outside the database system, or you can integrate it into the database system. That's a design decision that you make. And typically, of course, when you fiddle with these things, you can easily do it outside. I mean, you don't really need the structured query capabilities of the database system for doing stuff like that. It's just little things you need there. Yeah? So you can easily do it outside. Yeah? That's right. Yeah? But no one hinders you to do it inside and change the interface accordingly. Okay. Yeah, prepare query. Also as a repetition a bit from the BDE lecture again, check out SQL injection if you're not aware of that, but the main idea here is that you have an abstract query definition in SQL with placeholders for parameters, and you specify the parameters as separate lists. That's very important to get rid of SQL injection. And that's the standard way of executing a query. And the idea I implemented here in the interface is whenever you prepare a query, that you say, okay, that is my query, and maybe it has a condition where A equals $0, so where A equals placeholder, and then the placeholder is passed in a separate parameter, then you get an ID back. So basically the query is put into a dictionary by the database system, and then you're later on able to execute the query. This is done through a separate method here that's called execute prepared query. Here you see you don't pass a string of the query anymore, but you just pass an integer. That's the integer you observed, you received here in the first place while preparing a query. So the mechanism to execute a query is always you first call prepare query. You get an ID, and with the ID, you can actually execute the query and pass a concrete list of parameters. So here it's an abstract list saying, okay, there's a parameter C, there's a constant, and that's used in my where clause. Yeah? For instance, attribute A equals C, where C is the variable, the parameter, and you don't specify C. And then here you pass C to be equals 42, for instance. Yeah? And that's then internally translated into, aha, he wants to have the data where A equals 42. Yeah, that's how you prepare a query. So the parameters, the concrete parameters are separated from the remainder of the query. Yeah? But that's all part of the SQL injection video. Okay, right. Yeah, then if you have execute prepare query, you could also have execute prepared queries, plural. So you now don't have one query, but multiple queries actually. And on this you should work in the assignment of this week actually, because this method signature has some issues. If you think about that, some things won't work in this method. And part of the assignment is to think about what the heck is not going to work here. So I'm not going to go into that. But main idea is, okay, rather than passing a single query, as done here, query ID, and the parameters used for the query ID. Now I pass a dictionary. Yeah? So I pass the query ID, the prepared query ID, and the parameters. That's a separate type here, a nested class called query entry that contains the parameters for the query and the transaction ID where that query belongs to. So basically each entry here is the ID of the prepared query plus this query entry, which contains the parameters for the query and the transaction ID where this query belongs to. Yeah? And your job is to think about what the heck is going wrong here with that interface. Okay, yeah, that's it about the query interface. One part of the assignment will also be to think about what does it mean if you had a method that allows you to support a single transaction at the same time. Again, a query is a single statement, a single update, a single delete and whatnot. But what if you had a method that allowed you to support an entire transaction or a batch of transactions as part of the database interface? And that is what the assignment sheet or part of the assignment sheet for this week will be about. Okay, that's a queryable component. How are we doing time-wise? I think we have 5 to 7 minutes left. What else can I, maybe we can start already a little bit going into this one. Okay, so this is again the summary of what I just said. So we have a decorator pattern being implemented here. So the DBMS is an asset store and it has a reference to an asset store. Like that, we add additional functionality X to the wrapped asset store. And that is what the query optimizer is doing. So the query optimizer will add that additional functionality. Then we also extend the DBMS's API in that process by inheriting from queryable component. That is what this prepared or non-prepared queries is about. Basically a function allowing you to pass a query, whatever that means, and return some stuff back. That's the methods being added by queryable component. What I also changed is I factored out the interface of the MVCC store. So it's now called transactional something store. But there's an abstract interface for any type of asset store. It should implement that interface no matter how it is implemented. And that's factored out in the implementation. Yeah, the MVCC store extends, so it is a key value store. The key value store in the figure is not a separate layer. Yeah, so maybe just to clarify, because it looks a little bit like that. This looks like layers. Yeah, I scribbled it like that to say, yeah, it's not a layer I use as. I mean, it's kind of still a layer in a way, but it's the layering is done through inheritance. In inheritance, you typically extend the methods of the base class, of the super class. Yeah? You basically call super in the method, and then you do some stuff on those methods typically. And that's kind of layering. It's kind of wrapping and decorating the underlying methods as well. It's a similar thing, but it's not the pure layering that I mean by the layered architecture here. So if I have a layer here, that's typically not done through inheritance. That's the application layers something. It would also violate this idea that you can say is a. Yeah? So typically the application is not a database management system. The application has or is using a database management system, but it's not is a. There are applications that actually are database management systems. Yeah? So another database management system. Then it's okay, but in general you're not able to say that, and that is why you shouldn't be using inheritance here. Yeah? Okay, that's important. Yeah, and that's what I mentioned. Yeah? So we use other key value stores as persistence layer. Okay. What else? So do we have the main parts for the assignment? I think you know everything you should know. Let's make sure. Maybe in terms of code, you will see that now we have this interfaces directory. Yeah, already popping up some other directories that will come up in the next lectures, but that's empty on the main branch so far. You already see query optimization stuff that will come up eventually and query processing. So we try to bundle the interfaces now into this directory. But for the moment, the interesting thing for you to understand are these interfaces I mentioned, so the general asset store, key value store, and this queryable component. That's more or less a trick in modeling where I bind two interfaces together and then inherit it later on. And then they can use this directly later on in the code. Yeah, so far I would say we have all the material for next time, right? Let me double check, I don't forget anything. Yeah, we talked about all interfaces from this graphic actually, yeah? So now you already know about these interfaces here. I showed in the graphic, so you know this is an asset store interface, yeah, implemented here by the MVCC store. We have a key value store interface here. We have the query optimizer, different story. And next week we will extend this MVCC store or asset store to support indexing. But that's what we do next Wednesday. Yeah, see you then. Have a good weekend.